All right, everyone. Hopefully you can still hear me. And I'm Ananth, and I'm going to talk about my work on teaching robots using interactive imitation learning. So before we get started with how to teach robots, let's take a quick look at what I mean by interactive imitation learning. So there are three key pieces to interactive imitation learning, and that's effectively the environment, learner, and the teacher. We'll take a look at each of these pieces individually. So when we talk about the environment, we're essentially trying to formulate how the world works for the robot. And we make a key assumption stating that the world follows a Markov decision process, and this kind of gives us a way to kind of encapsulate the whatever's happening around the robot. So the first key element of a Markov decision process is the state. So this kind of gives information on how things are in the world. So for example, if I'm teaching this robot to pick up a cup that's placed on a table, the state would be where's the cup in the environment, where's the robot in the environment, and if there's a human involved, perhaps where's the human in the environment. It could also be things like, oh, is the gripper open or closed, things of that nature. The next is a set of actions, and the actions cover things like, okay, what can the robot do in the environment? So it could be provide joint velocity. So for example, maybe the robot arm is hovering in the air and it wants to go towards the cup. So it can provide these joint velocities that move it towards the cup. So the action would be providing these joint velocities. It could also be things like, oh, I'm at the cup, I want to close the gripper to be able to hold on to it. So things of that nature. Those are usually the actions. And then we have our transition function. So most Markov decision processes could also be stochastic. So this is some way of modeling uncertainty in the environment. So instead of saying if I'm in a particular state and take a particular action, I'll always end up in this state. We kind of have this probability distribution over a bunch of states that tell the robot, okay, if I take this action, this is likely where I'll end up, but here's some other options for states. And then finally, we have a reward function that kind of is used to steer the robot towards whatever it is that the human wants the robot to do. So for example, in this cup example, it could be that, oh, you get +5 when you pick up the cup. Maybe you get -10 if you drop the cup, things of that nature. So it's essentially a scalar function that kind of quantifies how good or bad the robot is doing. Okay, so moving on to the learner. So the learner is generally a robot, or it could be any agent, but for our work, it's just going to be a robot. And the robot's objective is fairly straightforward. It wants to learn a policy that maximizes the expected return. Here, the return or the reward are basically interchangeable. And generally, a policy is given by this formula. And the idea here is our function. And the idea here is, given any state that the robot is in the environment, it has to figure out what action it has to take to maximize the reward. So for example, again, returning to the robot arm hovering in space, what it wants to do is kind of move towards the cup. So it might get, the policy would be, okay, move me towards the cup. If I'm close to the cup, pick up the cup, etc. Things of that nature. So let's move on to the more interesting part of imitation learning and interactive imitation learning, which is the teacher. So in most imitation learning cases, we assume that there are no rewards given. Instead, it's something that the human knows inherently. That just we're not able to describe it mathematically as a formula for the robot to optimize. So instead, what the human does is they provide a set of demonstrations. These demonstrations are trajectories that kind of communicate what the reward could be. So for example, going back to our picking up a cup example, instead of writing down pick up the cup mathematically, what the human would do is teleoperate the robot to pick up the cup a bunch of times from a bunch of different locations. So that would be these demonstrations. And each trajectory can be thought of as a set of state and action pairs. So at a different state, the robot starts at different states, and then it kind of moves towards this cup. The robot is being steered by the human to do this, and these demonstrations are these collections. Later on, we'll look at cases where maybe we don't have access to actions or things of that nature. So we can make some modifications, but this is generally what imitation learning is. So that's for what we talked about is classic imitation learning. The idea is the human has a reward in mind. They cannot communicate it explicitly, so they show it through some demonstrations, and the robot has to learn. So that's effectively the idea here. And there's no other interaction between the robot and the human. So when we move on to interactive imitation learning, we open this problem up a little bit more. And the idea here is that unlike the previous case where the robot just was given the demonstrations and it's good luck, you do whatever you want. Instead, the human is available to help as the robot is learning. And they can provide feedback. So this feedback is generally two types. There are other types, but I'm going to mention two that are perhaps important here. So those can be corrections or preferences. When we talk about corrections, the idea here is effectively, let's say, going back to this picking up a cup example, the robot is trying to do it, but it makes a mistake. The robot is going in the opposite direction of where the cup is. The human could interject, take the joystick, and then like move the robot towards the cup. So it's not like a full demonstration per se, but it's more like a small snippet that's correcting mistakes in whatever the robot is doing. And this is happening as the robot is learning. And the next is preferences, which is slightly different. So in corrections, the human kind of like came in and interjected. The robot could also explicitly ask the human for help. And the idea here is it's going to try out a bunch of things in the world, and it has like no idea which ones are good or bad. So you can provide them to the human and be like, well, can you rank them or pick one that you like? So that's really the preference. It's kind of providing these rankings for all the things that the robot did. So that's how robots can learn from these scenarios. Let's take a look at the flip side of this, which is like, well, what role is the human playing in these scenarios? As we know, humans can be fairly diverse, and this leads to like incredibly diverse scenarios for learning. We'll explore this from two critical aspects in this research. There are, of course, other ways to do it, but this is basically what my focus was. The first focus was while looking at how important the human effort is to the robot's learning process. What I mean by that is, let's say there's this chef and there's a robot in the kitchen that wants to learn how to cook. So can the chef provide many demonstrations or a few demonstrations? Can we see like the impact, the amount of effort, which is proxy for like how many demonstrations the chef is providing, or could be anybody else, and if that has an impact. The next thing we're going to be looking at is the reliability of the interactions. What I mean by that is, like I was saying earlier, if this was a kitchen example, the chef is the one providing. He's considered to be an expert. On the other hand, if it was somebody like me who's not really an expert cook, now the reliability of the interactions may not be as good. And this is kind of independent of like the amount of effort. It could be that the chef is busy, they might only provide 1 or 2 demonstrations and leave, or they can also provide as many as needed. Simultaneously, I could also have the time to provide many demonstrations. My demonstrations will be suboptimal, but I can provide as many as needed. Or on the other hand, maybe I don't have time and I'll only provide a couple. So we have like this different scenarios that come up. In this talk, I'm going to talk about 3 specific cases. The first of which is probably the ideal case of like, there's a perfect demonstrator and they're happy to show as many demonstrations and corrections as needed for the robot to learn. Then we move on to like slightly more difficult scenarios where the demonstrator does not have time. So they just provide a single video demonstration and then leave. That's pretty much it. So we want to see if the robot can still learn from it. And then finally, we take a look at a special case where the demonstrator is able to provide as many as demonstrations as needed, but they're all really bad or like suboptimal. So we kind of want to see if the robot can still learn from these suboptimal demonstrations. Okay, without wasting much time, let's get into the first, which is learning from a bundle of optimal demonstrations and corrections. So where can we find such abundant optimal demonstrations and corrections? I want to make the case for assistive robot arms. So as you can see here, there's a person and he's trying to pick up this glass that's placed on the table. So this is effectively a daily task that this person is doing with this assistive robot arm. So as we can see, this person has used this arm several times, and they're really the experts in knowing how to operate these arms. So they've used them countless times, and they have the prerequisite knowledge to be able to show good demonstrations. And on top of that, since they're using these daily, they have this incentive to like provide corrections as needed. So if the robot, perhaps there's some autonomy involved, the robot is trying something, if it's making mistakes, the human is always there ready to correct it, and the robot can record these corrections. So I also want to highlight some like issues with these assistive robot arms. So in this particular case, this robot arm is being teleoperated using a joystick. And you can see it's extremely slow. This is because the joystick is generally 2 or 3 degrees of freedom, but the robot arm is at least 6 or 7 degrees of freedom. So because of this reduction in the degrees of freedom, it kind of makes it difficult to operate. Normally you have like a linear mode where you move in XYZ space, and then you have to switch to change the orientation and things of that nature, which you can see here. Here, he kind of moves linearly, and then now he changes the orientation to be able to hold it correctly. So it's kind of, it makes it very tedious for people to do it. So In that case, we were just looking at teleoperation, but we kind of want to see, well, how can autonomy help here? So this problem is generally shared, set up as a shared autonomy problem, where the idea is that let's assume that the robot knows that this person is trying to pick up this cup. And it's known somehow, somebody gave it, okay, I'm trying to pick up the cup, right? So when it knows this task, it can look back at the past and then it can try to assist the human based on this particular task that it was trained on. And the idea here is that instead of just having the robot run the full task or the human do the full task, we have this blending where both actions are acted upon. And they're kind of arbitrated using the confidence in like how good the robot thinks it knows the task. But of course, the primary issue here is, well, if you don't know the goals ahead of time, then you cannot use this, right? So this kind of like severely limits the use of shared autonomy. But we kind of want to look at a different perspective on this. Well, as we saw earlier, this person has been using this robot countless times, and they've been repeating these tasks all the time. Maybe they're opening doors, making coffee, whatever it may be. And we kind of want to see if we can reformulate this problem as an imitation learning problem so we can learn from these repeated interactions. So how can we formulate shared autonomy as interactive imitation learning? So let's assume that at some interaction I, the human has a desired task in their mind. Perhaps they want to open a door of some kind. So with this goal in mind, they start teleoperating the robot. And as this is happening, the robot can collect what the states are that the robot is visiting and what actions the human is giving. For countless such interactions, the robot can make a data set of these trajectories, which effectively cover, okay, some for opening a door, maybe some to make coffee, whatever it may be, just collects this data. So now at any given time, the robot knows three things, which is what state it is in, what is the trajectory that the human took so far, and it also has a data set of past trajectories that it can look up into. So given this setup, we want to see if the robot can learn from these past interactions. And we found that there's three main modules required for the robot to be able to learn in such scenarios. Those are recognize, replicate, and return. Let me walk through each one. So when we talk about recognition, the idea here is that given a bunch of interactions that the robot has seen before, we want to embed down into some latent space where they get distinguished. So for example, maybe there's 10 demonstrations opening a door, 5 to make coffee, etc. In this latent space, they're segregated. So when it sees a new demonstration that is similar to perhaps opening a door, now it's like, oh, I've seen this in the past. This is for opening a door. Once we get this, we kind of have an idea of, okay, this is a task that the human wants to do. And when we know, when we see this task again, let's say perhaps now the human is trying to open this refrigerator door again, it can look back into the past and then try to figure out what action would best help the human, because it has this repository of other tasks that it has seen that are similar. So effectively what we have is this encoding that helps us figure out what the task is, and then the decoder is our policy network that helps the robot like come up with the assistive action that is mimicking what the human did in the past. So thus far what we did is pretty good if it's a known task. So maybe you're opening doors, the robot is good at opening doors, we're happy to let the robot do it. But what if you're doing something new? So this is something that the robot has not seen before. Now, we kind of don't want the robot to interfere. It has to realize that this is a new task, the robot has no idea what this is, and it has to return control so the human can actually show the robot how to do this task. So we do this using a discriminator, and the idea here is that it kind of, the only job it has is to distinguish between seen and unseen tasks. And by doing so, what it's going to do is raise the confidence if it's a seen task. So maybe if you're opening a door, this is a seen task, it's going to be, oh, let's raise the confidence to 80%. Now we know what we're doing. But if you're picking up the cup, this is something it hasn't seen before. Now the confidence drops to perhaps 10% or 0% ideally, and then it's just observing and not providing any actions. So this is our method, and we call this method sorry. So once this method was kind of, we came up with, we wanted to try it in the real world, see how it works. So we did a bunch of user studies, but in the interest of time, I'm only going to talk about one. So in this particular user study, we had 3 different tasks that the robot had to learn. The first is picking up a lemon and dropping it in this pan. The second is picking up this can of soup and then pouring it. And the final one is picking up this spatula and then stirring this pan. So we wanted to see across these 3 continuous tasks if the robot can learn to do these tasks or replicate the behavior. And it's important to note that there's no other information given to the robot. All it got is like a bunch of trials that the humans did, and that was it. So there was no, oh, these are demonstrations for pouring, these are demonstrations for stirring, whatever it may be. So it's just, here's a bunch of demonstrations, and then you have to figure out the rest. So we wanted to figure out two different things here. The first was, well, if this is an unknown task, the robot has not seen this task, we wanted to make sure that our discriminator is working properly and returning control. And the reason for this is if you use these assistive robots, and if the robot is kind of very confident in the task it wants to do and doesn't let you do anything else, it kind of gets stuck in a loop and it doesn't let you operate the robot, which can be very, very annoying. So we wanted to avoid this problem with our method. So here we baseline against two pretty much state-of-the-art baselines here. The first is no assist, wherein like there's no autonomy involved at all. So this is basically the gold standard when it comes to unknown tasks. The human is just providing or teleoperating the robot. There's no autonomy involved of any kind. The next one is CASA, which is pretty much considered to be the state of the art in these kinds of like shared autonomy, repeated shared autonomy situations. The way CASA works is it kind of it comes up with a model for how the human works, and then it tries to fit in their actions into these models. So the idea is, let's say it saw a bunch of demonstrations for like picking. Now, when they're doing a different task, like the pouring task, the robot is going to look at the states and the actions that the human was visiting and then try to figure out, okay, if they were actually picking, is this an action that they would take? But the key here is that they have this model that kind of decides if this is a good action or not. And we used two different metrics to kind of compare our method to the baseline methods. The first was total time. The idea here is if the robot was not getting in the way of the human, then the total time required would be pretty much identical to no assist, wherein they're just teleoperating. That's the gold standard. We cannot do any better than the human's teleoperation by themselves. Directly tied to that is the mean confidence that kind of shows how confident the robot is in this task. So since it's an unknown task, the confidence has to be pretty close to zero to indicate that, oh, this is a new task, I don't know how to assist here. So across both of these metrics, we see that our method is fairly close to no assist and is miles ahead of CASA, especially in the mean confidence. And again, this kind of comes back to the rationality that they have and this model that they use for humans. Since they're using a model, it kind of restricts the kinds of actions they can take, and then the human can only perform in certain ways that is not realistic. And we found that it becomes a big hurdle in these unknown tasks. Next, we move on to known tasks. Here, the idea is it's the same task, but now there's a bunch of demonstrations collected. The robot has been trained. We want to see the opposite effect. So now it's an unknown task. The robot is going to try them, or the human is going to try them, sorry, and then the robot has to assist the human. So here, again, it's the same baselines, but we have two different metrics. The first is operating time, which kind of ties into how much input the human is giving, or like how much effort they're expending here. And the idea behind this is, let's say you're trying to pick up the lemon. If you recognize that the robot is actually going towards the lemon, you could just be like, okay, I'm not going to provide any inputs. The robot can just pick up the lemon. If you can only you might only intervene if the robot starts to make any mistakes. The opposing time is slightly different in that there are many folks who want to get there quicker. So even if the robot is moving, they might also provide their inputs. So in this case, we wanted to see if the robot recognizes the correct task, then it has to actually provide inputs that are very similar to what the human's inputs will be. And if they're opposing or fighting, then it kind of recognizes or wants to do a different task, which kind of adds to the time, the opposing time. So across both metrics, we see that our method is better than the baseline. And once again, this kind of comes down to like their rationality model is what we believe. Because of these restrictions imposed, what happens is in real time, as the human is moving, it's kind of confused, like, oh, is this a new task? Is this not a new task? And the confidence, again, is close to 50%. So it like sometimes assists, but towards the wrong goal, etc., things of that nature. So what are really our primary contributions in this work? I think the first is that we reformulated shared autonomy as an imitation learning problem or interactive imitation learning problem. And this kind of allows us to learn from history and interactions instead of like relying on these predefined goals that the robot can go to. And to do this, we introduced 3 modules that we think are necessary for the robot to be able to do it. Those are recognize, replicate, and return. So there are, of course, some drawbacks to this particular method. The first of which is that it's constantly collecting data. So, for example, let's say it's seen 10 demonstrations of me opening a door. It's an 11th demonstration, it doesn't know, it's just going to keep collecting. Despite knowing the task, it's just going to keep collecting data. So it kind of puts a lot of stress on the system in terms of like the data being collected. And as I was talking earlier, this only works if the human is an expert, right? Like, and part of it is like if the user makes mistakes. So for example, they're picking up a cup of coffee, they spill it, the robot will also just learn to spill. There's no like better than demonstrator performance. The best we can do is be very similar to the human. And on top of that, it also requires like a very high fidelity control interface, which is usually joysticks or like kinesthetic teachings or whatever else. But effectively, we need some way to like record states and actions in fairly close to real time. And this is the only way the robot can replicate the actions. So moving on to the second approach, we're going to relax this requirement for having a control interface that's like high fidelity and see if we can just learn from a single video demonstration. So what do I mean by that? Let's assume there's a video here of me trying to make tea. And all I want to do is just give this video to the robot and be like, just figure it out. The rest of it, I don't want to talk to you anymore, and then see if you can still run. So as you can see, there are a few key parts here. The first being that the robot is not involved in this demonstration at all. It's just me providing this demonstration, and we're expecting the robot to just learn by looking at this. And as you know, this is sort of how humans learn most of the time. When I was learning how to cook, I would just go on YouTube, kind of see what people are doing, try to replicate. We kind of want to tease out some of these learning methods to robots, so they can also do something similar. So effectively, what we want to do is give the robot this one video and then be like, okay, do what I get in the video. That's effectively our problem statement here. So what are some challenges in this setup? So this is usually called visual imitation learning. And the primary issue is that the robot has no idea what actions the human took or what states they visited. All we got is this bunch of frames with like pixels, and that's all the information that's given. And on top of that, there's no robot in any of the videos. So it has like no, morphologically, it's completely different. So for example, the human has perhaps different degrees of freedom, different dexterity based on like what gripper is being used, etc. So it's not like a one-to-one mapping to what's happening. And then finally, we're giving it a video, which is two-dimensional, but the world is three-dimensional. So there's some like loss in the data. And we try to deproject even using depth information. There's a lot of like noise introduced. In our experiments, the noise was usually at least 5 centimeters all the way up to like 20 centimeters, which if you're trying to manipulate objects is catastrophic. So how can still robots learn from such low fidelity data? So we found that there are, once again, 3 main components for robots to be able to learn here. The first of which is learning to extract a prior. The idea is the human gave us this video, which is just a bunch of pixels that have no meaning for us. We need to be able to extract something meaningful that we can use. And then this prior may not be good. Like we were talking about, there are some issues with the morphology, etc. So we need some way to compare what the robot is doing to what the human did in the video. So we need some agent agnostic reward function. And then finally, once we have this reward function, we kind of have to have a way to explore around the prior using this reward function. So this is kind of the 3 modules that we think are important here. So let's dig into each module. So the first is prior extraction. As we're interested in manipulation tasks, despite the video having many pixels and many things, really what's most important to us is what is happening with the human hand and the objects around them. So there's this existing neural network model called 100DOH, and using that model, we can isolate the location of the hand and if it's in contact with any objects in space. So across the entire video, we can extract the location of the hand and if it's in contact. Once we extract this, we can refine this a little bit further, because if you're just looking at the 2D hand location, that might not be sufficient information. So we can superimpose a 3D model of a hand and then get better insights into like where's the wrist, where's the index finger, etc. using this model called Nano. Once again, something that already exists. So using these models, we can get this trajectory for what the human approximately did. So this trajectory, while it looks good, there are a few key issues here. The first is that this is a lot of data. So for example, if I provide the robot with a 10-second video of me doing something at 60 frames per second, that's 600 waypoints. But if I'm just picking up an object, really, we don't need so many frames. And remember, we have to explore around these waypoints. So this adds up a lot. So we combine this with Squishy, which is like an existing compression algorithm. And the idea here is that given this very high number of waypoints, we kind of want to pick only the important ones. So for example, if I'm picking up and placing an object, all I want to know is where did the robot start, where did it pick up, maybe perhaps some intermediate points so I'm not hitting any objects, and then where did I place. And Squishy helps us get rid of all the other waypoints. And the way it does it is like it looks at each individual waypoint, tries to remove it and interpolate. If it can interpolate, it just gets rid of the waypoint. But at these key waypoints, you cannot interpolate and then still get the same trajectory. So an important question here could be, okay, we got this trajectory, let's just try it out, let's see what happens, right? So we could just be like the humans prior, let's try it out, what could go wrong? Well, like I was saying earlier, there are two key problems with this. The first is that the morphological differences kind of lead to questions like, well, what part of the human hand am I going to focus on? Is it going to be the wrist? Is it going to be the index finger, etc.? So because of this like ambiguity, it may not always go to like the ideal waypoint to pick. And on top of that, as we were talking about, the sensor noise like adds, or like the deprojection noise adds a lot of inaccuracies here. In this particular case, I think it's off by about like 7 centimeters. Like I was talking earlier, we've seen cases where it was off by 20, 25 centimeters. So once we have these waypoints, what is really our key goal here? We actually want to explore around the extracted waypoints and then kind of figure out, okay, how can the robot learn to imitate from here? So to be able to do this, we actually have to go back to our prior extraction and extract some additional information. And that is the object trajectory. And the reason for this is, despite us extracting how the human hand moved, that's not really what we're interested in here. We're actually interested in how objects change in the environment. So for example, if I'm picking up and placing a mug, what I'm really interested in is how the mug moved, not really how the human hand moved. So we need to extract like what object the human hand was in contact with, and then how it moved throughout the entire video. So given these two extracted from the prior, we have like the compressed hand trajectory that kind of gives a rough idea of what the human hand did. It's not perfect for us, but it's a start. And then we also now have the object trajectory. So it's important to get the object trajectory because that kind of directly ties into how we can get the agent agnostic rewards. What I mean by that is, like, as I was talking about earlier, what we really want to do is compare the object trajectories across videos to figure out if the task is successful or not. So if, for example, here on the right, I picked up the cup. On the left, you can see a couple of trials where it failed. And in one trial, it actually picked up. So across these videos, when it's comparing, the robot can look at the object trajectories and be like, okay, the first two I failed because I got low rewards. And in the final one, I actually picked up and I got high rewards. So the agent agnostic reward functions kind of come from like this idea of, okay, we have isolated the object and we're only interested in how the object is moving and not really who is moving the object. So moving on, now we have the two key pieces. The prior is extracted. We also have the agnostic rewards. So now we have to explore. But there are some issues with just trying to explore and like optimize for rewards here. The primary one is that this is a very sparse reward scenario. But what I mean by that is, as you saw in the previous slide, in a lot of cases, the robot is like nowhere close to the object. And because of that, it has like no useful rewards. Like every reward will be -10 or something like that. So it has no information on like how to optimize. So, and the reason this happens is because if you don't grasp the object, every waypoint we visit, we're just going to get 0 rewards or like -10, whatever it may be, they're constant. So that's why it's key that we split the exploration into 2 phases. First, we actually want to learn how to grasp. So that way, every waypoint we visit, we at least get some rewards. So the first phase is going to be learning how to grasp, and then the second phase would be actually doing the task. So let's take a look at each phase. So the grasp exploration, we kind of changed the setup a little bit here. Like I was saying earlier, this is a sparse reward scenario, and there are a few things that could happen here. The first being, in many cases, the robot just doesn't move the object at all, and it just doesn't get any rewards. The second case could be the robot moves close to the object, but it like hits the object. So now the object was moved, but it wasn't moved in the correct way. So the rewards would be like lower than what they were when it wasn't interacting with the object. But through experience, we know if the robot actually hits the object, then that's like a much better indicator that we're close to the solution than like the ones where we didn't have any interaction with the object. So we changed the objective a little bit for grasp exploration from can you optimize for rewards to like we want to encourage the robot to interact with the object as much as possible. And using this objective, we kind of force the robot to look for waypoints that are close to the object, because as it gets closer, it's going to start hitting the object more and more, and it's trying to like get more and more of these waypoints. So how do we set up this problem so we can use this new objective to explore? So what we do is we kind of take the waypoints from the trajectory of both the human and the object. So at the grasp location, we know where the human hand approximately grasped it. We know there are some issues with it, but we have an approximate idea where they said they did it. And then we also have like the approximate location of the cup, which again is not perfect, but it's kind of close. So what we can do is make a bounding box that kind of like encapsulates these points and a little bit of space around it. And we know that there are a bunch of points in here that will lead to a successful grasp. And we want to see how we can get there quickly. However, an issue here is that this space is continuous. So how can we make sure we actually grasp is kind of difficult, right? So we first discretize the space using centroidal Voronoi tessellations. And the idea here is that instead of looking at this continuous space and then trying a bunch of waypoints, we split it into these equidistant points and then try these equidistant waypoints. And remember that we're just trying to like hit the object. And if we hit, then we can locally optimize and then get the solution. So this kind of changes things for us a little. But once we do this discretization, there's no other information for us here. All we know is that one of these waypoints or a few of these waypoints will lead to success. So now the question becomes, okay, well, how do we pick which waypoints should we look for? So we found that instead of, like I said, we initially said it's all points are equally likely. So we could have just been like, okay, so let's just try randomly exploring. But we found that that doesn't work. Instead, we actually have to split the waypoints into two groups and use the information from our visited waypoints to help us. And the way we do it is that we set up these sets. All the waypoints that we've already tried go into the visited waypoints, and all the waypoints we haven't tried go into the unvisited waypoints. Then we have this distance metric that kind of computes how close or far all the waypoints in the unvisited set are from each waypoint in the visited set. Once we have this, we kind of maximize this distance to find the waypoints that's like far away from all the other waypoints. This kind of looks a little bit mathy, but let me explain it using this 2D figure that hopefully explains it better. So the idea here is, let's look at this 2D environment. At the top left, we have this black triangle that is the prior. Bottom right, we have this object which is the green star. So if you randomly explore, we can see the robot just randomly picks waypoints to try, and then there's a bunch of space at the top between the red black triangle and then the top line, and then around the green star that it hasn't explored. So it's not like even the way it's exploring. However, if we use our objective, you can see the robot is more systematic in its approach. So it continually tries the outside waypoints and then slowly goes inside and then tries more and more. And you can see at the end, it's kind of more evenly spread out the waypoints that it tries. So let's look at this in action. Here, I picked up the cup, and here the robot is trying. So the first waypoint, it didn't work. Here's the second waypoint that was slightly far away, that didn't work. And this third waypoint, which was wildly different from the other two, it actually worked, and the robot picked up. So this is kind of what we see when we try to explore uniformly in the space. So once we picked up, it kind of simplifies the process from here on. We know the rewards are continuous, so we can use any of our optimization algorithms to like solve for each of these waypoints in the rest of the trajectory. So if it's like picking and placing for each of the other points, so perhaps like excluding the pick point, it would be the intermediate point, the place point, etc. We just solve for them individually. And we can use Bayesian optimization to do this. We're not tied to Bayesian optimization. You can use any optimization. We just use Bayesian optimization. And this is the rest of it in action. So on the left, you can see I picked up and placed it. On the right, you can see it's trying a bunch of things to figure out, okay, what is the correct way? And then it finally figured out how to pick up and place them. All right, so now we tried this in the real world. We wanted to see if it would work with some real world scenarios. So here we tried 3 different scenarios. We wanted to pick up some objects, push some objects, and then move. So these are usually considered to be standard space for manipulation tasks. So here we have 3 baselines. The first is the prior itself. So we just wanted to try it, see if the robot can learn from it, or just roll it out and then see if it can do it. The next is world, which is considered to be state-of-the-art baseline here. And the key difference between world and ours is that it does not segregate between grasp and task phases. So once it gets the priority, it just like uses auto encoders to try and solve for the task. And then we have RSVO, which is an ablation. And the idea here is that we wanted to highlight the importance of this centroid-based method that we talked about earlier of discretizing the space and then seeing or like uniformly exploring it. So we look at the success rate, which is whether it succeeded in doing the task or not, and we do it for each phase, which is grasping the object and also completing the task. And as we can see, the prior never succeeded in anything. So as we talked about earlier, just rolling out the prior is simply not an option. When we look at world, it has some success in picking up the object, but it never it doesn't consistently succeed in doing the task. So what we saw would happen is that in a bunch of the cases, it would pick up the object, but then it like forgets that it picked up the object and then just tries a bunch of other options without picking up the object. So despite going to the correct locations, it doesn't have the object and doesn't get the good rewards. RSVO is like an interesting case because as we can see, it's a little bit similar to world in like the grasp success because it's only optimizing for rewards. It's random. If it hits the object, gets some good information, it can pick up, but if it doesn't, it cannot. But when it does pick up though, it always solves the task. So this kind of gives us the importance of this split and then like doing the grasp and task separately. All right, so what are the primary contributions in this part of the work? I think the first is that we kind of like somewhat succeeded in teaching robots to imitate from a single video demonstration. And we did this by like coming up with these modules that together help the robot do it. The first of which is like, how can we extract this compressed representation of what the human did? Next, we have these rewards, which are agent agnostic and help the robot explore. And then finally, we have this sample efficient exploration scheme for our task. And this sample efficient exploration comes from our distance-based metric, which helps the robot pick through points efficiently. So once again, let's take a look at some drawbacks of this method, of which there are a few. The first is that we need the settings to be identical between the human's demonstration and the robot. So if the settings change a little bit, maybe the object is in a different location, the robot will not work. On top of that, because of the way we're extracting the objects and their trajectories, it can only interact with one object at once. So if you want to pick up 2 objects at the same time, our method will not work. And then this kind of carries over from the previous case. If the human makes a mistake, the robot has no additional information to get better. It will just make the same mistakes. All right, so now we move on to the last case where we look at how we can learn from suboptimal demonstrations. So here the idea is, instead of just trying to replicate what the human did, we want to be better than the human. So what is a case for this? Let's assume that I wanted to teach the robot how to bring me a cup of coffee. What I wanted here is on the left. But instead of showing a good demonstration that shows that, maybe I keep spilling coffee and then trying to correct for it as I'm going along. We want to see if the robot can still learn from such demonstrations. So, unlike the previous cases where we were just trying to replicate what the human did, we cannot do that here. And the reason here is if we just try to replicate, we will also spill coffee. So instead, because these are suboptimal demonstrations, we kind of have to change our strategy a little bit. Instead, we actually have to look at the demonstrations and then try to extract a reward that kind of encapsulate what it is that the human did and optimize for that. So that way, hopefully, we can learn to do the task. So to learn this reward function, let's assume that there are a bunch of reward functions given to us, and we just have to pick which one is the correct one. And the way we can do it is using this Bayesian inverse reinforcement learning setup, where the human provided a bunch of demonstrations, and we kind of want to see, okay, given these demonstrations and a bunch of these reward function options, which one is the most likely option? And the way it does it is like it compares the demonstrations shown to all the demonstrations that the human could have shown and see, okay, if this is the reward functions, which ones would they have likely shown? And the key here is that we're kind of comparing it to all the alternatives that the human can show. If the alternatives are good or bad, that kind of like makes or breaks the method. So these alternatives are generally considered as choice sets. So let me explain or like provide some formal definitions for them. So let's assume that the human provides some demonstrations, and these come from their choice set. So that the choice set is effectively all the demonstrations that human could have shown, but they chose to show a few specific ones. And we kind of want to see why that's the case. Of course, the robot has no idea what this choice set is. It can only estimate this is. So let's call xi r like the robot's estimate of this choice set. So now, when we're estimating, the question becomes, well, how do we estimate this choice set? Should we, if the human shows us such a demonstration where they spill coffee along the way, should we assume that the human could have shown this perfect demonstration where they did not spill coffee, but instead chose to show the one where they spill coffee? Or should we compare against like alternatives where that's not really the case? This may be because the human couldn't show this spilling coffee, the demonstration without spilling coffee. And what we found out is that if you want to learn from suboptimal demonstrations, it is better to compare against similar or simpler alternatives instead of like assuming the human can show any demonstration. So we tried this out on the physical robot to see if it would work in real life. So once again, the task is pretty straightforward. We just want to teach this robot to bring us a cup of coffee without spilling it. However, in our demonstration, we keep spilling coffee along the way. So in Bayesian inverse reinforcement learning, which is what I showed you guys earlier, if we assume that the robot could have been shown any demonstration, which is we could have shown the robot a demonstration where we don't spill the coffee, the robot just learns to spill coffee as it's going along. However, if we underestimate the human's choice set and we say, hold on, if the robot, despite the human trying to spill coffee, perhaps that's the best they could have shown for not spilling coffee, the robot actually extrapolates and actually brings you a cup of coffee without spilling. So what are our primary contributions in this part of the work? Well, we kind of enable robots to learn from these suboptimal demonstrations where I was spilling coffee, but the robot was not at the end of the day. And we do this by allowing robots to generate like more realistic choices. So instead of assuming that the human could have shown any demonstration, we say, no, try to bring similar or simpler alternatives. And using only those, see if you can extrapolate more information. So what are some drawbacks to this particular method? Well, the first and perhaps the key is that we need a reward function. We need a bunch of options, and we can only pick one from the given options. So this kind of severely limits the usability of this. And on top of this, there's also like perhaps the human cannot demonstrate properly, but they could provide preferences or corrections, and we haven't introduced any framework for the human to be able to do this in this particular method. So that's all of the work that I did in the last 4 years. Let me summarize some of the findings using a few bullet points. Well, the first is that, as we've seen, it's kind of important to understand what the human can and cannot do and what their capabilities are before like learning or using their demonstrations to teach robots. And the first key thing here is that if we want to like not have this cumbersome situation where, there's only a certain area, certain tasks the robot works, others it doesn't, we actually have to if we know ahead of time that we're learning from high quality demonstrations, we can avoid this and then have the robot have like a built-in discriminator that allows it to arbitrate on its own. So this way we can like avoid, this is the training cycle, we're just showing the robot how to train, and then we deploy it and then actually use the robot. Next, when we want to learn from like some low quality data, like a video demonstration, it's very important that we split the task into grasp and task phases. And as we saw earlier, if we don't do this, what happens is that the reward function is kind of sparse, and then the robot has no idea how to explore. And then finally, if you want to learn from suboptimal demonstrations that the human provides, if you know ahead of time that they are suboptimal, we can compare them to similar or simpler alternatives for better learning outcomes. All right, so of course, a lot of my work has been submitted or published. A lot of this has been 3 conference papers, and then 1 journal that was submitted, and then 1 that's under review. And that's my talk on teaching robots using interactive imitation learning. and I'm happy to take any questions.
Okay, thank you very much, John. So first, we'll just take some questions from the general audience. So you guys, and if you guys, when you guys are wrapped up, we'll move on to the next.
Sure.
So Ananth can call whoever.
Sure, mine.
I have a question from the second section with the optimal demonstrations. So when the robot finds a trajectory that is successful, will it continue to try and increase the reward, or will it just kind of stop?
So are you talking about like the video demonstration or which one? Well, that was the second one.
The optimal demonstration of the grid, basically, when it was able to pick up the object.
Oh, I see.
It got a reward, would it stop there, or would it continue to try to?
So that really depends on like your reward thresholds. So you could set the reward threshold to be really high. So if it picks up, it's done. Or you could be like, no, I need you to be better than some threshold. It's going to continue to try to optimize.
The last part of your talk, when you're talking about learning from suboptimal demonstrations, I really like the idea that considering that not spilling the cup of coffee, removing from the human's choice set would prevent the robot from zoning in on just spilling the coffee.
Yeah.
And you give it similar demonstrations which also spill coffee.
Yeah.
But how do they guarantee that you eventually lead towards not spilling the coffee?
So that's a very interesting question. I had to cut some slides to talk a little bit more about it because of time. But the idea here is when you design these alternatives, you kind of want to look at a few of these parameters. So in this case, we already know the reward function has a bunch of features, and we kind of use them to like distort and then create these alternatives. So when you distort them, you want to create this data set that is like contains a lot of these options of like spilling, not spilling, etc. And depending on the quality of that data set, it either learns to extrapolate or not. So again, this kind of comes down to like you need to have a bunch of reward functions which have these features that you can choose from. If that answers, hopefully that answers the question.
Yeah, and then on top of it, I know this might be beyond what you worked on. Is there a way then for us to theoretically think about how this negative data set can be created so that we ensure that we go towards scaling, or is there any other work that's probably?
There's a few different ways to think about it. There has been other work that does this. I'll talk about that in a second. But in our own case, I kind of, again, omitted a few slides. And then we have the way we create these similar or simpler alternatives is by distortions. And we create these distortions either using noisy inputs. So we kind of take the original trajectory, distort it using some noise, or we kind of try to change the dead space between inputs. So for example, the human gave inputs at a certain frequency, we kind of like reduce the frequency and see if they can do the same thing, etc. So there's a few alternatives that way. Another way would be using like machine learning techniques. So for example, this was, I think, T-Rex or T-Rex, I forget, one of those from DS or Dan Brown. And the way they do it is effectively, let's say you get this data set and you want to train a policy that replicates exactly what's happening. But along the way, you can like save the model at different stages, which are worse than the ideal case, right? So, and you can use these to generate these alternatives. So there's a few different ways you can do it.
Yeah. I have one question that will be, I think, of interest to the general audience. Kind of as you're thinking about your research as a whole in interactive imitation learning, what do you see as like the missing piece or like the key question that the community needs to answer to move this forward? Or do you think there is?
That's an interesting question. I think there are a few different ways to think about it. One could be individually for each of my works. There are like different questions that could be answered. For example, when looking at the videos, there are a bunch of like restrictions. Oh, the video has to be, you need to be able to see the hand and things like that. But like overall, I think the field, in my opinion, is fairly large, like interactive imitation learning. And we're only looking at robotics here. It could also be used for agents of any kind. And that kind of like creates this open space where it might be hard to define, okay, well, this is the key problem that we have to solve. It might be more like, it's a little bit like, I guess, the AGI versus non-AGI debate, I think, because people are saying there's one way to do it all, but in my opinion, there's just smaller cases you want to solve. And then what you really want to do is like try to figure out how to put them together. So as a whole, the system can figure out, okay, which of these methods can I use? For example, here, we already assume the human is good here, the human is bad here. But if you try to figure out, okay, can we have some type of like test that tells us what kind of human there is? That gives us more information, like, okay, what techniques can we use to improve? I guess that would be my hierarchical setup, ideally.
Right, John? Okay, if there's no other questions from the general audience, well, thank you guys. If you guys would mind leaving the room,
Feel free to get some donuts.
yeah, you can go. That's yes.
Just take the box. You're all going to the same thing.
Yes.
Yeah.
Okay. Thanks. All right, Dr. Hamid and Dr. Williams, thank you again for attending this presentation. Hopefully you can hear me okay. I'll turn it over to you both. I mean, obviously I've worked along with Ananth and I'm very familiar with this work. So I'll turn it over to you guys. Whoever would like to go first, please take it away.
I have a list. I'm happy to start.
Sure.
Okay, excellent. So I can begin with what I think is obvious, which is to compliment you on an excellent presentation. I mean, yeah, this is my opinion, but out of the presentations I see, I think this is very close to the top. So well done. A very clear impact, clear problem, clear solutions. Excellent. So what that generally means in these cases is that I don't have too many specific questions. I'm going to ask some more general questions. So, but let's get the little nitpicky stuff out of the way first. So can you go to slide 26? I think that the 26 is one of your studies.
Sure, I can pull it up. 26 is this?
Yes, 26. So you're running a human factor study, essentially, right? Did you use surveys afterwards to gauge human frustration? And the reason I'm asking this question is because what I'm seeing here, and actually this leads to a deeper question. I'm seeing here that there is still operating time, for example, in orange, where the human has to interact, right? Or the human has to take control and do something, correct? And if I'm misinterpreting this plot, let me know, but I believe that's what this is saying. And so I wonder, is the human still frustrated at, I guess the way to read this is 20% time that they still have to lend a hand, right? Is this something that you know from the study or not?
So this is a great question. We did multiple studies, and in the interest of time, I skipped a few. So for the first study, we did have a Likert scale. It wasn't like explicitly talking about frustration, but it was more like, would you prefer to use this method? Did you like this method? The questions are all lines. So I think could be proxy for were you frustrated or not. In this particular case, so the initial 20%, I think, is a bit more complicated than just saying the human has to still operate. That's required because in the beginning, the robot has no idea what you want to do, right? So you have to provide at least some inputs for it to be able to like, oh, this is the task. So we kind of have this dead time for about like a second or a second and a half that we technically counted as operating time because it is the human providing inputs, but it wasn't part of like, okay, the robot has started the ball rolling. So this kind of like the dynamic.
Okay, so that's an important factor actually. So let me ask, with that in mind, let me ask the deeper question here, which is, ideally we drop the orange bars to 0. Yes.
Well, as close as possible, yes.
Well, as close as possible, right? How do you think we move in that direction?
So I think there are, well, a few different things I can think of here. The first could be like better interfaces. So for example, here we're using a joystick. And then there are also some like very specific user study issues or like the experiment design issues. In our case, a lot of the objects, you had to move forward first. right? And then you can like branch out depending on the object. So as you're moving forward, the robot has no idea. Well, it's equally likely you want to pick any one of the objects. Okay? So there's issues like this, which I think on some level perhaps could be solved with like better interfaces. I don't know what that would be like, but maybe the neural link works and now you have a better way. Or it could be like AR, VR related ones. One of the ideas I had was instead of like physically trying in the real world, perhaps you have this like AR headset and the robot like rolls out in there, like what it wants to do, and then you can like choose. So in that sense, at that point, you're not like physically operating the robot, you just like look at it through the AR headset and then you pick the options. So there's things of that nature in terms of interfaces, which I think would help. But in terms of like our particular setup, unless we have like, I don't know, other ways instead of joysticks, it's probably hard for me to think of a way to like bring it down to lower. It probably could get lower, but perhaps the 0 might be difficult.
Okay.
Also not mine.
Yeah, interesting answer. I in particular, I like this idea of AR. I have this feeling that there are others who would be interested in this idea.
Sure.
Okay, excellent. The only other specific question that I had was regarding, now I failed to write down the exact slide number. I think it was 40 something, but it's the place where you're talking about grasp exploration, I believe. Yeah, basically the discretization and the effectively the sort of the I guess it's a sort of cost function in some sense. Okay, so I'm fine with the discretization, totally reasonable. But what occurred to me is that, okay, so initially it appeared as if all points are equal, but then you introduce this metric, which essentially means that that's not true. But this is so this doesn't confuse me mathematically at all. What confuses me a little bit is it seems to me that a very basic distance metric is not capturing the essence of a grasping task. And thus, is it really, we'll say, assigning a reasonable metric for one point is better than the other point when it comes to exploring for grasp? This was my problem here. And you have to keep in mind, I'm not at all an expert in grasping. So don't interpret this as an expert opinion. But I guess it's more of a, hey, help me here. Help me understand why this metric is reasonable for exploring a space for grasping. This was not clear to me.
So that's a great question. I think we can think about it in a few different ways. So let me try to like justify my thought process behind choosing this particular distance metric. So despite us like just trying waypoints, there's actually deeper information here, right? So for example, I picked up a waypoint in the trajectory and then I'm moving along that way. It's actually an arc that I'm making, right? And along this arc, there are many waypoints that I've tried but not really tried because the object hasn't moved. I've tried a bunch of these waypoints. So now what that kind of leads to is like, well, okay, we have this kind of bounding box. Any point could be likely, but with each arc I'm making, I'm covering a slice of the area. And what I'm seeing is in this particular slice, I haven't like, hit the object at all. So now this kind of leads into, okay, so let's try to do more slices in different areas to see if we actually hit the object, right? So, but how do we make these slices? And that comes down to this distance metric where the idea is, let's say I tried a slice here in one corner of the space. Maybe I want to try the other corner. And as I'm going, now it's like, well, I'm not hitting anywhere, and I've sliced a large areas off. So now I want to see if I can do something that's completely different and see if we're still hitting the object. So that was kind of like the thought process behind this distance metric. Can there be better metrics? I think there are a few different ways to think about it. We could also actually just use neural networks as part of this. We haven't done it just because of time and other things. But the idea there would be, you could just train, let's say you have this camera set up in simulations, and then you could be like, let me run 1,000 simulations, right? We just collect the information on like the robot trying a bunch of things, and then seeing if it's like hitting objects or not. And this kind of gives us like an affordance map that tells us, okay, if the object is here in space and the robot arm started from here, here's like possible regions where we actually hit the object or like interact with the object. So but again, that kind of introduces, okay, we have to learn this other piece. But if we can do something of that nature, now that like removes this need for perhaps a simpler way or like the simplistic way of just using this.
Okay. Yeah, I think that's a great answer because, yeah, you're right. You would have to train something else, right? But it's a more complex solution. I mean, it's a trade-off, right? You have something very simple here, very simple metric. It appears to work, but you could maybe do better with a more complicated solution. I think that's a reasonable answer, right? Okay. Yeah, my intuition here is that this is, I mean, it's obviously a heuristic, but I wanted to understand the underpinnings of why this may make sense for grasping. Okay, good. Okay, that's all I had in terms of specifics. We've seen this stuff in the prelim. So now I really want to go for the more abstract questions and see how you handle these. And the first, I think you touched on a little bit, and this may have even come up in the public discussion. That was a little bit hard to hear, but I'm interested in generalizability. So what I'm interested in is, so I have a demonstration for a particular task, right? And let's say that task lives in a class of tasks, similar tasks, right? Is your method going to, I expect that it doesn't work because, for example, in slide 33, just to throw out a particular point here, yeah, so I guess you're close enough to 33, we can make it. Yes. This setup is incredibly specific, right? So how do you generalize? This was my concern. So where are the points where you can there's a potential for generalizability?
So this is a great question, and then I kind of talk about this in the paper that we submitted as part of the limitations. So the idea here could be we actually need something that comes after this. So for example, most policy-based learning, imitation learning methods require like states and then actions to be able to run. So they really need the actions, which is what is missing, right? Using this setup for a bunch of demonstrations, we could learn, or like we can find out, okay, this is what the human showed us, but really this is the state action pairs that we can get to be able to solve this task. Let's assume it's pick and place, but we did it for a bunch of these different tasks. Now we get this data set that has been converted from human demonstrations to robot demonstrations with state action pairs. And then we can use like any behavioral cloning or like inverse reinforcement learning policy as an add-on. Now that will be more general because effectively the pipeline works as, okay, here's a bunch of demonstrations of people doing something. I'm going to first try to imitate exactly what they did. And then later on, I'm actually going to like improve upon this and like try to generalize by like collecting this as the data. Or like
excellent. Yeah, great answer. Okay, yeah, it's not like I had a specific solution in mind necessarily. I just wanted to hear you riff, essentially. Well done. Okay, funny enough, the final general question I had here, I think relates in some sense to what you were just saying, and it's this idea of learning or training others at scale, right? And what occurred to me is okay, this makes a lot of sense to use some synthetic data when you can. Will this work for your problem? Can I synthesize this teaching and learning problem in some respect? And to be slightly more specific, can I have the human use a simulation for the sake of demonstrating and then learn in that simulated environment and then do a synth to real transfer? Does this work?
So the way I'm understanding it is, let me try to put it in my own words and see if you agree. The idea is instead of like learning directly from these videos, the human shows a bunch of these demonstrations in simulation.
Yeah, and let me motivate as well. I can connect to a simulation from anywhere. I cannot demonstrate in real life from anywhere. Right. Just to give a single example, right? Yeah. So I'm trying to think about the idea of demonstrating and teaching at scale, right, versus having to be in a room with an autonomous agent.
So I think that's kind of the complementary problem of what I was trying to solve here specifically.
Okay, yeah.
The idea is I'm in the room with the robot and I want to just give a video, right? That's the only thing. We're looking at speed here, not necessarily like generalized predictive, right? Mm-hmm. In this particular case, I think our method does it in about like 20, 30 minutes. Most of the baselines do it like at least 6 hours, and half the time it fails after 6 hours, right? So that was really the focus. But when it comes to scale, I think what you suggested is perhaps more scalable, but it brings with it its own problems, right? For example, if you think about like real to sim transfer, that is not, or sorry, sim to real transfer, or vice versa, really. That's not really like a solved problem, right? It's an open area of research in its own.
Mm-hmm. Mm-hmm.
And as we were thinking, like I was thinking about it at some point, but it kind of becomes like, just as I was specific here saying, oh, the setting is specific, these are the object interactions, transferring them to simulations are not trivial. So for example, I have like a piece of cloth or like this rubbery substance that I'm trying to use, right? In the physical demonstration, there's a little bit more leeway for me to like encapsulate its physics versus like, oh, I just try to go do it in simulation. Now that requires a lot more effort in terms of like figuring out, okay, well, how do we model this? And then this adds this overhead in being able to do it, right? So it's kind of like this trade-off between like perhaps generalizability and then speed is what I'm thinking.
Great answer. I was thinking along the same lines. I mean, it's worthy of thought, but yeah, I agree. I think it may be incredibly difficult. But then, yeah, again, this idea of just asking how can you scale this, I think leads to, I don't know, potentially interesting topics to explore in the future. Okay, like I said, great presentation, really excellent work. That's all from me. Thank you.
Really helpful from the prelim to make it better.
Yeah, it was great. Thanks, Ananth.
Of course.
Thank you, Ryan. Dr. Ahmed, would you like to ask your question? Thank you.
Sure. So thank you, Dr. Losey. So Ananth, great presentation. I would like to echo what Dr. Williams mentioned. And so I really enjoyed your presentation, and you have published in high quality journals. And so I see the improvement compared to the prelim exam. And I went through your dissertation document, well written. I see the mathematical contributions there. I like the proofs, the propositions you have. So, pardon?
I had to skip them for the talk.
Yeah, I was just looking. I like math portion more, so just I took a look at that. So, and so nice work. So I have a question. So again, this is just a general question. So for example, in this slide 33 that you have. So from my understanding, as you mentioned, so you have three contributions, or you have categorized it in three different scenarios: optimal demonstration with correction, suboptimal with no correction, and single video demonstration with no correction. So in these demonstrations that you have, so for example, I see you have the wrist trajectory extracted or the object trajectory. Are these trajectories are mainly done in the Cartesian space or also in the vector, wrist angles are also extracted? I am asking to see, let's say you did the demonstrations in the task space, how you translate those into the joint space?
So that's a great question. Let me pull up a specific slide that I think will help me answer that. So the way it's currently set up, it is just XYZ. And the reason for that is this discretization, right? And the issue here is if you look at orientation is not a field, right? So when you go from like 360 and 0 are effectively the same degrees. So that creates like a lot of issues in like trying to split or like find equidistant waypoints. So in that's why we narrowly focus on just XYZ Cartesian positions to be able to do it. As soon as we go to degrees, that kind of adds this complexity. However, after I submitted the paper, or well, sort of kind of working on it, but we didn't add it, I did work on this, on including orientation, because if you want to teach manipulation, you require orientation to be able to do any reasonable task. And we solved that by considering orientation in terms of like the Rodriguez formula of parameters. So you have three parameters, u, v, and theta. All three of them are continuous, like u and v are 0 to 1, 0 to 1, and theta is like -5 to 5, or 0 to 360. by setting that restriction, I actually did the math and then kind of figured out that we can do this separation to get these equidistant points. But of course, that's only one part of the problem. The other part that I haven't figured out is, and this is probably the easier part actually, now that I think about it, is the object trajectory. So the object trajectory, we're only looking at the centroids as a way to compare the trajectories. So here, this is just like the XYZ positions. But let's say I'm pouring something. So now the centroid might be in the same position, but I'm actually rotating the object, right? So now I have to figure out a way to get the orientation of the object and involve that in this as well. So for that, there are of course some convolutional neural network-based methods, etc. I just haven't like personally tried them yet, but there are options to extend this to include orientation.
Yeah, exactly. Yeah, thank you. So yeah, because I was asking, you know better than me, right? So that we have, let's say, if it is a redundant robot, this translation or even for grasping from Cartesian space to the joint space may have infinitely many solutions or multiple solutions, let's say. So I was wondering, for example, the robot you are using has 7 degree, you can correct me, 7 degree of freedom or something. So I just want, yeah. Okay, yeah, I just wanted to see how do you do this trend. But there was also one comment and that also mentioned by Dr. Williams. It is related to that. So, and these demonstrations, as you see, you get the trajectories, let's say in the Cartesian space for, from the human demonstrations. But for some tasks, as you mentioned, for example, if you want to pour coffee or something, the dynamics also matters, not only the trajectory, the position trajectory, like that.
Right.
So maybe learning that dynamics, I don't know, maybe Dr. Williams mentioned maybe kind of human dynamics in simulation, but maybe force data, maybe some sort of understanding that dynamics that describes this pouring phenomenon, or if it is interacting with an environment, the force profile, those kind of stuff can also, I'm just thinking maybe more rich data can help the robot to learn better for future work, not definitely. But what are your thoughts about that?
So I have actually thought about this earlier a little bit. Again, I couldn't do it because I ran out of time. But essentially, one of my ideas was, well, here part of the thing is we have no idea how to translate from a video to like states, and we're using these existing models as a way to like as crutches to get there, right? But now, as you've said, that kind of ignores dynamics. We don't get actions, we just get states. We kind of have to make a lot of assumptions, etc. One of the thoughts I had was, well, what if we set up like a pure simulation with a bunch of these objects and the human interacts, we get the videos, and now we have this one-to-one mapping to the states in the videos or like the pixel locations, and also like what the human did in simulation, right? So now that we have this, we can train like some supervised model, which kind of learns, okay, so if this is the video frames that or these are the video frames that I see, then I kind of like, okay, so this is how I extract this state information. It could include like dynamics, it could include pretty much all the things that we can think of that we can model, really. But this kind of brings up like a couple of different questions. One being, again, if the dynamics are hard to model, like soft touch objects or stuff like that, now that kind of adds a lot of complexity in the simulation. So that was one consideration I was having. And the other one was, we also have to like think about like the transfer learning here, right? So because we trained it for a specific camera with specific properties, for a specific type of human, which is the simulated human, and for a specific robot, and the states were extracted. So now we kind of have to see, well, okay, can this be generalized to other robots and other people? I did find some work here that I was looking at probably like 6-7 months ago from Google DeepMind that kind of does this kind of work. And the way they do it is they have this very unique simulation where they just get rid of the human and the robot and then just have the objects move, and they still extract the states and locations and dynamics. So using that like unique simulation, they were able to extract this information. I haven't personally tried it, but I think that could be, so there's some like thought in like trying something like that to be able to extract more state information instead of just like, oh, this is the human's hand location.
Nice.
Simplicity.
Yeah. Fantastic. So I think these are my 3 questions for today. And again, great presentation. I enjoyed that, and I think you have done everything perfect. So I don't have any other comment. Thank you.
Great. Thank you both for your help.